case, that if we treat people's immune response to change the immune response to infection, we can improve their chance of surviving. So as an intensive care researcher, studying ways to modulate the host response to infection, this dexamethasone result is a little bit like someone walking into your office and banging a coelacanth down on the desk. It gives us a really strong reason to believe that we might be on the right track with other infections too. Now, the focus of the research that we're doing is to look for genes that are responsible for individuals being particularly susceptible to infections. So we've seen that there's always variation in the response to the infection. Well, a great deal of that is based in your genes. And I showed this slide last year. I love this study from 1988, which compared your chance of dying of one of these 3 types of disease if you're adopted, and either your adoptive or your biological parent died of the same disease. So if you if you're adopted and your adoptive parent, the person who brought you up in a certain environment that somehow presumably led to you having certain disease risks, if they died young of a heart attack or a stroke, then you're about 3 times more likely to die of a heart attack or a stroke yourself. And if your biological parent died of a heart attack or a stroke, then you're about 4.5 times more likely to die of a heart attack or a stroke yourself. So that's an index of the risk they conferred upon you by passing on their genes. For cancer, your adoptive parent's mode of death has a much bigger influence than your biological parent. So the environment in blue has a bigger influence than your genes in red. And for any infectious disease, if your adoptive parent, the person you called mum or dad who brought you up, who probably coughed on you during their final illness, if they died of an infection, then you're no more likely to die of an infection than anyone else in the population. Whereas if your biological parent, someone you might never have met in your entire life, died of an infection, then you're about 6 times more likely to die of an infection yourself. So that tells us that your susceptibility to infection is encoded in your genes. The answers are in there. But the trouble is that these answers are like needles in a haystack. So there are 3 billion letters in the code of the human genome. And finding an answer in amongst all of those, finding a difference between one group of people and another, that is to say, a group of people who have a disease and a group of people who don't, or who are just representatives of the population, is extremely difficult. And so in order to do that, we need to get very large numbers of people. There's not really another way around that. We can try various clever statistical techniques, and I'll mention one at the end. But fundamentally, we just need very large numbers of people, which means we need to recruit over a large area for a long time. And we also need to focus on the people who are most sick, in whom we'll see the biggest effect. That is to say, the people who are the very most susceptible in the population. And that's what we're doing with the genomic study. It stands for Genetics of Mortality in Critical Care. It's been running for 4 years, and we've been recruiting patients with sepsis in critical care. So patients who are critically ill, needing organ support with ventilators or ECMO or other treatments to keep them alive with sepsis. We're focusing on relatively young and healthy people who have no other explanation for why they're sick, and we're recruiting globally. So we're encouraging critical care doctors in other countries to recruit. And so far we're recruiting in Canada and Ireland as well as in the UK. But for just now, I'm going to focus on the UK because that's where I think we've had the biggest impact. So this graph shows our setup of the study back to 2019. So we'd already been recruiting for a few years in Scotland in 2019, but not even in every centre in Scotland. And this was just kind of a period when we were applying for funding to try to expand the study. And it was then when we had these ideas, but we were quite a small study with big ambitions, that the Fiona Elizabeth Agnew Trust, Sepsis Research, engaged with us and very generously supported us. So that second vertical line there on the graph back in July of 2019 is when the funding started from the Fiona Elizabeth Agnew Trust. And at that point, the blue line shows the number of intensive care units, or actually the number of beds covered by those intensive care units in the UK that we'd contacted. So we got in touch with lots of intensive care units and asked them to participate. And the orange line shows the number that are actually set up and recruiting to the study. And you can see that there are a few administrative procedures that you have to go through before a study gets set up. But we were kind of gradually expanding. And our objective, of course, was to get to the kind of 4,000 to every intensive care bed in the country. And then COVID hit. And of course, we were already recruiting when COVID hit. And in addition to sepsis, we'd specifically said in our design of the study, any patient with an emerging infection such as SARS or MERS or Ebola would be eligible for inclusion. So we started recruiting patients straight away when the outbreak started. And we applied for funding from the government. Now, the funding from the Fiona Elizabeth Agnew Trust was always intended to be a foundation for further applications for funding from other sources, because genetics is actually extremely expensive. But just as an index of how useful that money was, we invested it in that first year to get the study up and running. And because it was running, we were able to recruit patients with COVID.